Welcome, fellow explorers. Today we embark on a captivating journey through the Big Bang Theory. This isn't just any theory, it's the groundbreaking concept that seeks to explain nothing less than the birth and evolution of the universe. Picture this. All matter, all energy, everything that exists, compressed into an infinitesimally small point. Then in a moment of unimaginable intensity, the universe begins. An explosion not in space, but of space itself, expanding and cooling over billions of years, forming galaxies, stars, planets, and eventually us. The Big Bang Theory, first proposed by Georges Lemaitre and later supported by Edwin Hubble's observations, has revolutionized our understanding of the cosmos. It's a story of cosmic proportions, a tale of origins, and a testament to human curiosity. So brace yourselves as we travel back in time to the very beginning of everything. Our story begins not in the distant past, but in the early 20th century, a time when the understanding of our universe was about to be forever altered. This was the era when the seeds of the Big Bang Theory were sown. Belgian physicist Georges Lemaitre was one of the first to propose this radical theory. In the late 1920s, Lemaitre suggested that the universe was expanding from a primeval atom, a concept that was far from accepted at the time. He likened it to a cosmic egg, exploding at the moment of the creation, a theory that would later be dubbed as the Big Bang. Around the same time, American astronomer Edwin Hubble was also making groundbreaking strides in the field of cosmology. Through his meticulous observations, Hubble discovered that galaxies were not stationary, but were instead moving away from us. And not just haphazardly. The farther a galaxy was, the faster it was receding. This was empirical evidence of an expanding universe, a cornerstone of the Big Bang Theory. However, the Big Bang Theory didn't gain widespread acceptance overnight. It was a steady accumulation of evidence over the course of decades that solidified its standing. Observations of cosmic microwave background radiation, the detection of primordial helium and hydrogen, and the discovery of quasars all provided crucial support for the theory. Each discovery was a piece of the puzzle, gradually revealing a picture of a universe born from a singularity, a point of infinite density and heat. It was the relentless pursuit of knowledge by these early scientists that led to a profound shift in our understanding of the cosmos. They dared to challenge the status quo, to question the nature of our universe, and in doing so, they opened the door to a new era of scientific discovery. These pioneers set the stage for a revolutionary understanding of our universe. Their work laid the groundwork for much of modern cosmology, and their legacy continues to inspire scientists to this day. And while we have learned much about the universe since Lemaitre and Hubble's time, the quest for knowledge is far from over. The Big Bang Theory continues to evolve, driven by the tireless efforts of scientists around the world, each striving to unravel the mysteries of our cosmos. But what exactly is the Big Bang? Imagine, if you will, that all the matter in the universe was once compressed into an incredibly tiny point. This point, smaller than a subatomic particle, was incredibly hot and dense. It was a seething, indescribable mass of energy, with no stars, no galaxies, no space, and no time. Then, approximately 13.8 billion years ago, a cataclysmic event took place. This tiny point exploded with unimaginable force. This explosion is what we now refer to as the Big Bang. But it wasn't an explosion in the traditional sense, with a center and things flying away from it. Rather, it was an explosion of space itself, an expansion on a cosmic scale. In the immediate aftermath of this explosion, the universe started to cool and expand. As it did, the energy in the universe began to transform into particles of matter and antimatter. These particles annihilated each other, but not completely. For every billion pairs of particles, one particle of matter survived. These surviving particles are what everything in the universe is made of today. Over time, these particles of matter came together to form atoms, primarily hydrogen and helium. These atoms were drawn together by gravity to form stars and galaxies. Within the stars, the process of nuclear fusion began, creating the heavier elements that make up the world around us. This process of star formation and nuclear fusion continued over billions of years, leading to the creation of billions of galaxies, each containing billions of stars and untold numbers of planets. This is the universe we live in today, a vast and complex place of unimaginable scale and beauty. And so, from a singular point, our vast universe began to form. But how do we know this theory holds water? That's a great question, and the answer lies in the observational evidence that supports the Big Bang theory. This evidence is like a jigsaw puzzle, with each piece providing a different perspective that helps us understand the bigger picture. First off, let's talk about cosmic background radiation. This is the afterglow of the Big Bang, a faint whisper from the very early universe. It was discovered accidentally by Arno Penzias and Robert Wilson in the mid-20th century. They found a mysterious uniform noise coming from every direction in the sky, and it turned out to be the echo of the Big Bang. This cosmic microwave background, or CMB, is a snapshot of the universe when it was just about 400,000 years old. Now, the CMB isn't just a uniform glow. When we look closely, we see tiny temperature fluctuations. These are the seeds from which galaxies and clusters of galaxies eventually formed. The patterns in these fluctuations match incredibly well with predictions made by the Big Bang theory, providing a strong piece of evidence that our universe began with a hot, dense state. Next up is the evidence from the expansion of the universe. This was first observed by Edwin Hubble in the 1920s. He found that galaxies are moving away from us in every direction, and the farther away a galaxy is, the faster it's moving. This suggests that the universe is expanding, like a loaf of raisin bread rising in the oven. The raisins or galaxies are all moving away from each other as the dough or space expands. This expansion isn't just happening now, it's been happening for billions of years. By running the cosmic movie backwards, so to speak, we can extrapolate back to a time when everything in the universe was packed into an incredibly dense, hot state. This is another strong piece of evidence for the Big Bang theory. Finally, we have evidence from the abundance of light elements in the universe. The Big Bang theory predicts that in the early universe, conditions were just right for the formation of light elements like hydrogen, helium, and lithium. And when we look out into the universe, we find these elements in the exact proportions predicted by the theory. So, cosmic background radiation, the expansion of the universe, and the abundance of light elements all point to the same conclusion. The Big Bang theory provides a compelling explanation for the origin and evolution of our universe. It's not just a theory plucked out of thin air, but one built on a foundation of solid observational evidence. Each piece of evidence strengthens our understanding of the Big Bang. We're putting together the cosmic jigsaw puzzle piece by piece, and the picture that's emerging is of a universe that began with a bang. From the Big Bang, the universe evolved in stages. As we delve into the complex tapestry of cosmological models, it's important to remember that these are the frameworks that allow us to understand the universe's evolution post-Big Bang. One of the most influential models is the theory of cosmic inflation. This theory posits that a fraction of a second after the Big Bang, the universe underwent an exponential expansion. It's as if a grain of sand suddenly inflated to the size of a galaxy. This rapid expansion smoothed out the universe, leading to the largely homogeneous and isotropic cosmos we see today. But the universe didn't stop evolving after inflation. Instead, it cooled and expanded at a more leisurely pace. This phase is known as the radiation-dominated era because the universe was so hot and dense that it was filled with a plasma of photons, electrons, and baryons. As the universe continued to cool, it entered the matter-dominated era. The energy density of the universe was now dominated by matter, not radiation. This shift allowed the first atoms to form about 375,000 years after the Big Bang. This event, known as recombination, led to the cosmic microwave background radiation that we can still detect today. But the universe was still a pretty dull place at this point, filled with a nearly uniform gas of hydrogen and helium. It took another few 100 million years for the first stars and galaxies to form, in a period known as the Epoch of Reionization. From there, the universe has continued to evolve, with galaxies merging and stars forming and dying in a cosmic dance that's still ongoing. Today, we're in the dark, energy-dominated era, where the expansion of the universe is accelerating due to a mysterious force known as dark energy. These cosmological models are not just theoretical constructs. They're grounded in observational evidence, from the cosmic microwave background to the large-scale structure of the universe. Each new piece of data helps us refine our models and gain a deeper understanding of the universe's history and future. And yet, there's still so much we don't know. We don't fully understand what caused inflation or what dark energy is. We don't know what the universe's ultimate fate will be. Will it continue to expand forever? Or will it eventually contract in a big crunch? These questions are at the frontier of cosmology today. As we continue to observe the universe and develop new theories, we're constantly updating and refining our cosmological models. It's a bit like trying to solve a jigsaw puzzle where the pieces are constantly changing. These models give us a roadmap of the universe's incredible journey, from the initial singularity of the Big Bang, through inflation and the formation of atoms, stars and galaxies, to the mysterious dark energy that's driving the universe's expansion today. It's a story of cosmic evolution that's as fascinating as it is complex, and it's a story that's still being written. The Big Bang Theory has far-reaching implications. It's more than just a story about the birth of the universe. It's a roadmap that helps us understand the cosmos and our place within it. Let's start with the age and size of the universe, which are both directly linked to the Big Bang. By tracing the universe's expansion backwards, cosmologists estimate that the Big Bang occurred approximately 13.8 billion years ago. This makes the observable universe about 93 billion light-years in diameter. Remember, the universe has been expanding faster than the speed of light, so it's much bigger than its age might suggest. The Big Bang Theory also provides a foundation for understanding the formation of chemical elements. In the seconds following the Big Bang, the universe was an extremely hot and dense soup of particles. As it expanded and cooled, protons and neutrons began to combine, forming the first atomic nuclei in a process known as nucleosynthesis. This process produced hydrogen and helium, the two lightest elements, which make up most of the matter in the universe. But the Big Bang Theory doesn't stop there. It's also linked to the theory of cosmic inflation, which suggests that the universe underwent a period of rapid expansion shortly after the Big Bang. This explains why the universe appears flat and homogeneous on large scales, despite the uneven distribution of galaxies and other cosmic structures. And then there's the theory of dark energy, which posits that the universe's expansion is not just continuing, but accelerating. This unexpected finding, discovered in the late 90s, threw a curveball into our understanding of the universe, and it's still a hot topic of research today. In essence, the Big Bang Theory is a launching pad for countless other theories and discoveries. It's a cornerstone of modern cosmology that helps us decode the universe's past, understand its present, and predict its future. These theories continue to push the boundaries of our cosmic knowledge. So, what does all this mean for us? Well, the Big Bang Theory offers us a compelling explanation for the origin and evolution of the universe. It's a testament to human curiosity and our relentless quest for understanding our cosmic home. This theory, supported by substantial observational evidence, tells us that our universe began as a hot, dense point nearly 14 billion years ago. From this fiery birth, the universe has been expanding and cooling, giving rise to galaxies, stars, planets, and ultimately, us. It's also given birth to numerous cosmological models, like the theory of cosmic inflation, helping us to understand the universe's behavior and its various stages of evolution. These models and theories are not just academic exercises. They are the foundations of our understanding of the cosmos. The Big Bang Theory has profound implications. It's reshaped our perception of the universe and our place within it. As we continue to explore the cosmos, the Big Bang Theory remains our guiding light.